Welcome to another deep dive. Today, we're going to be looking at, well, it's a pretty big one. The fundamental theorem of calculus.
Yeah, it's a big one.
I know, bit of a mouthful. But it's a foundational theorem. And I think it's really cool because it connects two ideas that seem very separate.
Yeah.
Like figuring out how fast something changes, the rate of change
Right.
with like the area under a curve.
Yeah, and what's really fascinating is for centuries, those were thought of as completely separate things.
Right. Totally separate.
Like if you go back to the ancient Greeks, they were already using ideas that today we would recognize as integration.
Oh, wow.
Like they had this concept of infinitesimals, these infinitely small things
Yeah.
to like calculate areas.
Okay.
But it took a really long time, like centuries, for people to make the connection between that and the idea of differentiation, like figuring out the slope of a curve, the rate of change.
So someone had like a real aha moment at some point in history.
Yeah, a big one. So like the fundamental theorem of calculus really comes down to saying that those two ideas, finding the area under a curve
Right.
and finding like the slope of that curve, they're actually inverse operations of each other.
Oh, okay.
It's kind of like, I don't know if this analogy works, but it's like saying if you know the exact shape of a hill,
Mm-hmm.
you automatically know like how steep it is at any given point.
Oh, that's a great way to think about it. So it's like they're two sides of the same coin.
Exactly. And that realization, once people figured that out, it just changed everything in calculus.
Yeah.
Because suddenly all these things became connected and it had huge implications, not just in math, but in physics, engineering, economics, like any field that deals with change and accumulation.
That's pretty wild. I mean, when you put it like that, it sounds pretty fundamental.
It really is.
Okay, so now that we've got this kind of basic idea, I'm curious about the actual, like, the formal statements of this theorem.
Right.
Did someone just, like, neatly write them in a textbook one day?
Well, not exactly. I mean, it was a gradual process.
Huh.
But eventually, the fundamental theorem of calculus kind of crystallized into two main parts.
Oh, so there's two parts to this.
Yeah, two parts.
Okay, sounds like things are about to get more complex.
Well, I mean, it sounds complex, but the concepts themselves, I think, are actually pretty intuitive.
Okay, good.
So, like, the first part, which is, rather unimaginatively called the first fundamental theorem of calculus, it essentially says that if you take the derivative of a function's integral, you get back the original function.
Wait, hold on. Let me just make sure I understand that. So we're talking about finding the area under a curve, which is the integral, right?
Right.
And then finding the slope of that area, which is the derivative.
Yeah.
And somehow that circles back to where we started.
Yeah, think of it as like a mathematical round trip.
Okay.
You start with a function, you take its integral, then you take the derivative of that result,
Mm-hmm.
and you end up back at the original function.
Okay. I think that's starting to make sense. Can we, like, visualize this round trip somehow?
Sure. I mean, imagine like hiking up a mountain trail and then back down. So you exert all this effort going up, you accumulate elevation gain, right?
Right.
And then on the way down, you undo it. You end up back at your starting point.
I see. So, like, the integral would be, like, the total effort and elevation gain.
Yeah,
And the derivative would be, like, how steep the trail is at each point.
exactly. You got it.
Okay, so that's the first part. Now, what about this second part?
Okay, so the second part of the theorem, which is sometimes called the second fundamental theorem of calculus, or the Newton-Leibniz theorem, it basically gives us a powerful tool to actually calculate those definite integrals.
Okay.
So remember, a definite integral, that's where we're interested in the area under a curve between two specific points.
Right, so not just any area, but, like, a specific slice of it.
Exactly.
Okay.
And the theorem tells us that to find this area, what we need to do is figure out the antiderivative of our function.
Oh, antiderivatives. Now, that sounds familiar from, like, way back in calculus class.
Yeah.
But I could definitely use a refresher.
Yeah, sure. So simply put, an antiderivative is basically a function whose derivative is the original function.
Okay.
So if our original function describes the slope of a curve,
Mm-hmm.
the antiderivative describes the curve itself.
So it's like we're working backward from the slope to reconstruct the entire path.
Exactly.
Okay.
And this is where the second part of the theorem becomes really handy, because it tells us that if we can find the antiderivative of a function,
Uh-huh.
we can calculate the definite integral just by plugging in the boundaries of the interval into that antiderivative and then subtracting the results.
Oh, so it's like a shortcut?
It is a shortcut.
That sounds way easier than trying to, like, calculate that area directly.
It often is. But here's where things get a little bit interesting.
Oh, there's always a but.
There's always a but in math. So the way we usually use this second part using antiderivatives to calculate integrals, that's actually just a corollary. It's like a consequence of the more powerful second fundamental theorem.
Wait, so there's like a shortcut to the shortcut, or like a more robust version?
Yeah, there's a more robust version, exactly. And that's where the true power of the full second fundamental theorem really shines. You see, the corollary, the shortcut that we usually use, it relies on the function being what we call well-behaved, meaning continuous over the entire interval.
Okay.
But what if we encounter a function that's not so well-behaved?
Like a function that's a little unruly, a little, discontinuous.
Exactly, discontinuous. The shortcut can't really handle that.
Okay.
But the full second fundamental theorem, it can. It's like having a more powerful tool in your mathematical toolkit that can handle those trickier situations.
Okay, so now I'm really intrigued. Can we see this heavy machinery in action? Like, can you give me an example of when we'd actually need to use the full power of the second fundamental theorem?
Absolutely. Let's dive into an example.
Okay, so give me an example then, where this shortcut, fails, and we need the full power of the second fundamental theorem.
All right, imagine you have this function, right? And it's pretty smooth, predictable in most places. But then at one specific point, it just takes a sudden jump.
Okay.
It's like discontinuous at that point.
Like trying to measure the length of a path, but then you suddenly get, teleported a few steps forward.
Yeah, that's a great analogy. So our shortcut, the corollary, it kind of assumes that we can smoothly measure things along the whole path.
Right.
But when there's a jump like that, it gets thrown off.
So it can't handle it.
It can't really handle it. But the full second fundamental theorem, it's more flexible.
Okay.
It can account for those discontinuities.
So it's like it has a built-in teleportation feature.
Exactly. It can handle those jumps and still give you the right answer.
Okay, that's pretty cool. So instead of getting bogged down in a really complicated example, the takeaway here is that the theorem can work even when things are, discontinuous.
Right. And that just speaks to how powerful it is. It's not just about these, simple, well-behaved functions.
Yeah.
It's really a deeper truth about this relationship between change and accumulation.
I'm starting to see why it's called fundamental.
It is. And to really drive that point home, I think it helps to think about the physical intuition behind it.
Okay. Yeah. Let's get concrete.
So imagine a car driving along a road.
Okay.
And we know the car's velocity, right? Its speed and direction.
Mm-hmm.
So the velocity, that's like the rate of change of the car's position.
Right. Okay.
Now, if we integrate the velocity function over a period of time, what we get is the total distance traveled.
Okay, yeah, that makes sense. Because we're adding up all those little changes in velocity over time.
Exactly. So integrating the rate of change gives us the total change. That's the second fundamental theorem in action.
Oh, wow, that's cool. So it's like summing up all those little tiny steps the car takes to see the overall journey it took.
Yeah. And it works the other way around, too.
Okay.
The first fundamental theorem, remember that one?
Yeah.
That tells us that if we know the distance traveled as a function of time, we can figure out the velocity at any point in time just by taking the derivative of that distance function.
So we're retracing the car's steps to figure out how fast it was going at different moments.
Yeah, exactly. So you see this simple example with the car. It shows how these two ideas, rates of change and accumulated totals, are really intimately connected.
Yeah.
And the fundamental theorem of calculus gives us that framework to understand that connection.
All right, so that car analogy, that really helps solidify it for me.
Good.
So what else is there? What else does the outline have in store for us?
Well, it seems like we're ready to move beyond these basic examples and think about how the fundamental theorem of calculus extends to, more complex scenarios.
Okay, more complex. Does that mean we're venturing into uncharted territory here?
In a way, yeah. I mean, the theorem was initially formulated for continuous functions, but it turns out we can actually generalize it to a much wider class of functions, even functions that aren't continuous.
Oh, wow.
And we can even think about it in higher dimensions.
Higher dimensions, we're going beyond just the flat world of our graphs into 3D, 4D.
Exactly. So, instead of just the area under a curve, imagine the volume under a surface.
Oh.
Or even higher dimensional analogs of that.
So we could calculate volumes, hypervolumes, all sorts of things.
Yeah. And the core principles of the fundamental theorem, they still apply.
Okay, that's pretty mind-blowing.
It is. And even within single variable calculus, there are these fascinating generalizations. For example, there's something called Lebesgue's differentiation theorem.
Lebesgue's differentiation theorem.
Yeah, have you heard of it?
That sounds pretty advanced.
It is a little bit more nuanced, but basically it deals with a more general type of integral,
Okay.
and it can be seen as kind of a broader application of the fundamental theorem.
So it's like the fundamental theorem is like a seed
Yeah.
that grows into a whole forest of related concepts and theorems.
I like that. That's a great analogy.
So it's not just one thing.
No, it's not just one thing. And the outline mentions a few other really interesting connections, like connections to Taylor's theorem, the divergence theorem, the gradient theorem, all of which kind of build on these ideas from the fundamental theorem of calculus.
It's amazing to think that one theorem can have so many implications. Like we've just peeked through a tiny keyhole into this vast mathematical landscape.
Exactly, and that's the beauty of math, right? It's all connected.
Yeah.
And the fundamental theorem is just one stepping stone on that journey.
This has been incredibly enlightening. Like I'm starting to get a real appreciation for how powerful and far-reaching this theorem really is.
It is. It really is.
So as we kind of come to the end of this deep dive,
Yeah.
are there any like final pearls of wisdom you want to leave our listener with? I feel like we've been through a lot. From those aha moments
Yeah.
to like the formal statements and all those
Mhm.
examples, even the really mind-bending ones. It's pretty fascinating stuff.
It is, yeah. It sounds like you've got a really solid grasp of the fundamental theorem now.
Yeah, I think so.
But as with any deep dive, there's always more to explore.
Absolutely, yeah. So before we like come up for air from this mathematical ocean,
Right.
are there like any final pearls of wisdom that you want to leave our listener with?
I think one of the biggest takeaways here, if we really zoom out and look at the bigger picture, is that, the fundamental theorem of calculus, it's not just a formula, right? It's really more like it's a lens through which we can view the world. It's a way of understanding how these tiny, almost imperceptible changes can accumulate over time to create these really big, significant effects.
I like that, yeah. Infinitesimal changes leading to big effects.
Mm.
It's almost like that the butterfly effect.
Yeah.
How like a butterfly flapping its wings can cause a hurricane on the other side of the world or something.
Exactly. Yeah, it's all about that interconnectedness of things. And this idea, it applies not just to math, but to so many aspects of life.
So what are some real world scenarios where our listener might actually, apply this kind of thinking?
Well, think about something like personal finance, for example.
Yeah.
The way that small, consistent investments over time can lead to big wealth growth.
Right.
Or in physics, the way that a small continuous force applied to an object can accelerate it to incredible speeds.
So it's about understanding that sometimes the most significant outcomes, they come from these like consistent incremental efforts.
Exactly. And the fundamental theorem of calculus gives us that mathematical framework to understand that, to even quantify it. It's like having a secret decoder ring to understand how these small changes can build up over time.
It's pretty powerful stuff. I bet our listeners like ready to go out and see the world through this new mathematical lens.
I hope so. The fundamental theorem of calculus is really a gift that keeps on giving. The more you explore it, the more you kind of uncover its beauty and its power.
So before we sign off here, any final like thought-provoking questions you want to leave our listener with?
Yeah, how about this? What other everyday scenarios can you think of where this idea of integrating these infinitesimal changes where it applies? How does this concept change your perspective on things that unfold over time, whether it's, the growth of a tree or the evolution of an idea?
Those are great questions. I really hope that this deep dive has sparked a curiosity in our listener to keep exploring this amazing world of math. It really is a journey of endless discovery.
Absolutely. And remember, there's always more to learn, more connections to make, more aha moments out there waiting to be discovered.
Couldn't have said it better myself. Thanks for joining us on this mathematical adventure.
It's been a pleasure.
Until next time, happy exploring.